3. Hi guys, okay, one of the most beautiful and important equations that I know is Bayes' law, how to compute conditional probability. And I even tell my students that I will upgrade their final score on my courses if they tattoo Bayes' law on their arm. But my guest today, who is much smarter than me, and his understanding of Bayes' law is much more profound, will try to convince me today that I'm wrong, and I'm afraid he's going to succeed. Hi, and welcome to my show, The World of Roy Yosevich, when I speak and host the most interesting people from all around the world to discuss science, religion, philosophy, artificial intelligence, and probability. And my guest today, and this is a true honor, is Professor Yehуда Pearl, or as his parents called him, Yehuda Pearl. Now, Professor Yehуда Pearl needs no introduction in the field of computer science and artificial intelligence, but since not all of my viewers comes from this field, so he is a computer scientist and a philosopher. He is the father of Bayesian networks and the guy who is responsible for developing a theory of causal and counterfactual inference based on structural models. He is a recipient of the prestigious Turing Award, and it's like the Nobel of computer science for, and let me quote, fundamental contributions to artificial intelligence through the development of calculus for probabilistic and causal reasoning. And is the author of several books, including The Technical Causality, Model Reasoning and Inference, and most recently, The Book of Why, a book on causality aimed at the general public. And we cannot escape, and we don't want to escape, another major part in his biography. Yehуда Pearl is the father of the journalist Daniel Pearl, Hashem Yikom Damo, who was kidnapped and murdered by terrorists in Pakistan simply because he was Jewish. So, Professor Yehуда Pearl, thank you so much for coming. How are you today?
I feel great, Roy. Thank you for having me on your show.
Okay, so I have so many things to ask you, but with your permission, I would like to start with Bayes' law. And I think, or I thought, up until I read your great article, I thought that Bayes' law is one of the most profound and important theorem in probability, because Bayes' law, what meant to me was the idea of subjective probability and the idea that we can change our belief based on the models, based on the measurement. I can change my prior belief based on the measurement, based on data, based on reality. And I thought that this is remarkable and this was important. But you referred me to a great article of yours, which called Bayesianism and Causality, or Why I'm Only Half Bayesian. Now, I read a lot of papers, and first let me tell you, this paper is poetry. It is so well written. This is, it's like an example of how a scientific paper should read. So with your permission, I would like to read the first paragraph. It's a very short paragraph from your great paper, and we will start from this. And you said, and you can say it, and you can see it, I turned Bayesian in 1975, and soon as I began reading Savage monographs, The Foundation of Statistic Inference. The argument were untenable. One, it was plainly silly to ignore what we know. B, it is natural and useful to cast what we know in the language of probabilities, and if our subjective probabilities are enormous, their impact will get washed out due time as the number of observations increases. 30 years later, I am still a devoted Bayesian in the sense of 1, but I now doubt the wisdom of 2, and I know that in general 3 is false. Wow, so many things. So basically what you say, and let me just see if I got it right, in Bayesian theory, if you have more measurement, the prior distribution or the prior probability is just washed out because you keep get measurement from the environment. And there, what you say in your book, the subjective aspect of probability basically become an objective. And you say, this is not correct, this is false. So could you please elaborate on this point? Because this is crucial. And I've teaching Bayes' law for 5 years, and I never catched it.
Yeah, maybe perhaps I can show an example where you can take zillions and zillions of data points and your prior will not be washed away, okay? So let's take an example where you have two models. One says that the rooster crow makes the sun rise. And the other one says, no, it's the sunrise which
makes the rooster crow.
Makes the rooster crow, yes, and it goes through some glare in the atmosphere which the rooster senses, okay? Now we are going to test the two. How we are going to test the two? We just put prior. I'm more inclined to believe, because I'm subjective and I want to play devil advocate. So I put 70% chance that the rooster does affect the sunrise, okay? And 30% chance that it's the other way around, okay? Now let's take data. We observe
say it again and again and again and again and again and again.
Again, and you wouldn't tell them apart. Okay? Why? Because for every incidence of the two variables here, sunrise and rooster crow, they fit well, the two models. They fit the model alike, just equally strongly. Okay, so you wouldn't be able to tell them apart. Now, what's wrong here? And does it defy the wisdom of a Bayesian network? No, it's simply that the difference between the two models is a difference between two causal models, not between two probabilistic models. Okay? Bayesian is very nice in distinguishing two probability models, one from the other, but not between two causal models.
Just a second, two causal models that can be written in the same probability mathematical notation.
I'm sorry, I have to stop you here. We are talking here about a third dimension, which all the studies of probabilities in the past 20 centuries, right, has not captured. You can be a great probabilist, and I know many statisticians, but they cannot capture the new dimension. This dimension is dimension of causation. You think about it as orthogonal to the two dimension in which we work. Think about it as a three-dimensional component, while we live in the Plato cave of silhouettes. Okay? We see silhouettes on the cave wall, and we do not capture the three-dimensional nature of the object which throws its shadows on the wall. So if you think about it as the third dimension, I think it's a good metaphor here. So here I'm making a strong statement that all the probabilists, all the statisticians, more than that, all scientists, okay, from the time of Adam and Eve until in Abraham, he was the first scientist, okay, until today, and still have not captured the idea of cause and effect relationship because they didn't have a language to say X causes Y.
And this is one which is say that in the basic, on the formal notation of probability, we can't write A causes B, and not even with conditional probability, and we go into this later on, we can say, okay, the probability of A given B is greater than the probability of A given not B, therefore B causes A. This is not the same thing, but you make another great observation in this article, and you say basically the world of science, yes? And let me just read. Bayesians turn extremely suspicious when the same judgment is cast in plain English, as if mud doesn't cause rain. And basically what you say that Bayesians think or want to think in the terms of the equations, but scientists don't want to think in terms of cause and effect. And you said, I have a co-viewer on a paper I've read recently offered the following objection to the causal model postulated by the author. And she said, you postulated a causal model, I can offer another different causal model, so I don't want to talk about causality in the realm of science. It's like scientists afraid of speaking about causality. Why?
Oh, first of all, scientists are the most conservative species ever inhabited our planet. Okay? They are paid to exploit their training in the best way possible. And since they grew up on the language of probability, they will adhere to that language tooth and nail. So that's number one inhibition we have. And maybe it's the most important one. So it's a matter of learning a new language. You know, it's a traumatic experience. You know, I said that people go to war about languages. They don't go to war about bread and butter. They go to war about languages. Look about all the religious war, okay? What are they fighting about, okay? You say that Muhammad was the greatest prophet, and I say, no, it was Moses, okay? It's just a metaphor, and we're fighting bloody battles about this metaphor. Because it's quite traumatic to change languages. So that is the main reason that scientists cannot shift to this new language, although they use this language in the cafeteria. Okay?
And they think about their experiments using this language, because what causes this phenomena in my experiment? And they think because we are built in to think in cause and effect. We don't think in correlation, we think in cause and effect.
Absolutely. Actually, we are very bad correlation computers. We are much better cause-effect computers. Every child can tell you whether it makes sense or learns how to distinguish a toy that rattles and from a toy that doesn't rattle if you shake it, okay? So they are extremely cause-effect tuned, whereas the equation of physics and the probability was imposed on us by a great statistician and probabilist. I can go from Fermat to
Francis Galton and Pearson.
Huygens and Pearson and Galton, but we are more familiar with names like Bernoulli, okay? Extremely ingenious, actually almost prove the law of large numbers.
Yes.
And without which we wouldn't have statistics and we wouldn't have the idea of distribution. And so these were great scientists which put probability theory on our table and in the mind of every other scientist, but it is not the natural language in which you design experiments. You design experiments using a hypothetical model of the world. And my favorite example is Eratosthenes. Okay? Eratosthenes in about 200 BC decided to measure the radius of the world. Okay? What gave him this idea? It wasn't a theory of celestial motion.
It was a letter that he got that the sun was just in the solstice in Alexandria, I think, and in just noontime, the sun was, when he looked into the well, so the sun was just above him. So he computed, because he knew that in the solstice in Athens, I think, so it was like 3 degrees. So he computed the radius of Earth. By the way, he was the guy who coined the term geography.
Well, thank you. I didn't know that. Yeah, but no. The main point is that he envisioned this experiment on the basis of totally wrong picture of the world. He believed, like all the Greeks, that we are walking on a turtle shell, okay? And the radius that we see, right, is a radius of the turtle shell. The sun, the stars were not objects. The stars were holes poked in opaque shell through which we see the eternal light. The Greek picture of the world was totally wrong, but it was metaphorically meaningful. What does it mean? It means that it gave rise to new experiments. And that's what leads him to believe, why? If we are working on a turtle shell and we have a radius, then I can measure the difference between the 2 angles, okay? One in Alexandria and one in Aswan, near the Aswan Dam, okay? And since I know the distance, I'll compute the radius, okay? So this is my perfect example of the difference between the Babylonian perception of science, which was care-fitting, and the Greek perception of science, and how the latter, which is built on metaphorical analysis, give rise to creative experiments, which the former one did not. Okay?
And you need the cause and effect in this particular thing. Now let's move from this, let's move on to your latest book, The Book of Why. And I want to start with the beginning, with the introduction. And in the introduction, you write something, again, poetry. When I write equation, let me just show it to everyone on YouTube. Just a second, 1, 2, 3, share screen. When I write equations, I have a very clear idea of who my readers are. Not so when I write for the general public. An entirely new adventure for me. Strange, but this new experience has been one of the most rewarding educational trips of my life. The need to shape ideas in your language, to guess your background, your questions, and your reactions did more to sharpen my understanding of causality than all the equation I've written prior to writing this book. Wow. Now, one thing that when I wrote my book about intelligence, The Unpleasant Truth, I found that the most challenging thing to explain to the general public was the concept of overlapping distributions. The idea that on general, men are taller than women, but there are many women which are taller than many men. The idea of overlapping distribution in the context of IQ was extremely hard to explain. So I have 2 questions. What was the hardest thing to explain to the general public in the world of causality? And 2, what was the most important insight that you got from trying to explain causality for the first time to the general public? I told you I came prepared.
Yeah, I think everything was nice to explain, was easy to explain. Because of the principle that we think causally. So the examples could come up so easily. I don't have to manufacture them artificially just to fit the science. Okay? So I had a wealth of examples, and my major challenge was to not to appear controversial.
Not to appear controversial.
Right.
I think you are old enough. You can appear whatever you want to appear. What do you care?
Yeah, but you see, what I advocated would sound heretical. because I'm telling students essentially, forget about what you learn in your undergraduate statistics course, okay? You have to acquire a new language. Statisticians are misled and so on. So this is a quite heretical kind of messages that some people read, and I was intensely clubbered by statisticians who felt the honor of their profession is being attacked. And not to speak about economists. Economists are the worst, okay?
I had a talk with Daniel Kahneman recently.
Yes, yeah, no. Daniel is a good economist. He's open-minded. I think because he served in Tzahal.
Yes.
Okay, yes. But you take ordinary economists, and nothing you can say that would please them, except that everything that was ever done was done by an economist.
Now, do you think that 10 years from now in the computer science department, in statistic 101 or probability 101, we will see a different syllabus, or we will incorporate the causal modeling in for computer science students, for undergraduate computer science students?
We already see that happening. Universities are beginning to offer classes in causal reasoning. UCLA, my university, has 3 classes in causal reasoning.
Undergraduate courses?
No, graduate. It's graduate. Yeah,
but
graduate.
I knew what I asked. I asked specifically, would you think that this theory will boil down or will come down all the way to the undergraduate training of the computer science industry?
Not because I think only. I'm talking about general education, statistics, and social.
Yes, definitely.
Absolutely. Look, eventually it will be. Look, how long can statistic instructors resist the curiosity of his students when students read the book of why, or when students ask him, what do you mean by correlation, coefficient, regression analysis? Okay, undergraduates spend maybe 3 or 4 weeks on regression analysis, and the instructor talks causation and writes down correlation on the board. So, and this kind of tension, okay, is obvious to every curious student. How long would they be able to cheat their students about the fact that they think causation and they write correlation? Not too long. Okay.
Okay, so I think that we need, with your permission, to start at the beginning. Now, when we think about the philosophy of causality, it makes sense to start with David Hume, as a Scottish skeptic who famously said that one cannot see causality in nature, only correlations. Only correlation, and this is like I think that Hume is a good starting point. And now I have one question. Do you think that Hume got it wrong, that we can see causality in nature? Or Hume got it right, and we need Immanuel Kant to say, yes, we don't see causality in nature. We come built in with the causal eye. What do you think about Hume observation that we don't see causality in nature?
Well, first, he is right in the sense that observing nature passively without intervening doesn't give us any clue about the world as we understand it, okay? We don't see causality. You cannot go from passive observation to causal models or to causal assertions without something else. Something else could come in 2 forms. Either you have a preconceived idea of what causes what in the world, which is fine, it's called causal model. The other one, you have intervention. Okay, you have experiments you can run, and you can control. And that is also very ancient technique, but Hume did not hang on the intervention. Okay, he just said you cannot do it. However, 9 years, I believe, after he published his first treatise
of human nature.
Let me see. I have the first edition here, so you wouldn't.
What do you mean first edition? From the 16?
Yeah. Here it is, first edition.
Treatise on human nature, which is a great piece of prose. Hume is a great English writer.
But he is great, yeah.
But just a second, Yehuda, Hume was familiar with the concept of interventions, but
no, I haven't seen it in his writing. He doesn't bring that as a factor for his theory of causation. However, what he did 9 years later, he totally changed his mind, although I don't believe he noticed that he changed his mind. We notice today. So he said he shifted from correlation to counterfactual. He said, let's think about, I forgot, it's a beautiful passage. He said, had object not being the same, okay? So let's think about, so he talked in counterfactual language to explain causation as an alternative, because I bet he noticed in these 9 years that his theory, that causation comes from correlation only, is deficient. We know that it is deficient because we have confounding, and he didn't, okay, as an example, I go back to the rooster and the sunrise. You have a perfect correlation there, yet even Hume would not say that the rooster caused the sun to rise, okay? So there is deficiency, and he corrected it. He repaired it by referring to counterfactual. Had the object not been there, I forgot exact, I should have kept in my mind. I quote it in the book of Why.
Just a second, let me open it. Just a second, okay. Okay.
Read it because it's beautiful and it's very instructive.
I will try to look for Hume. Okay, so, but what you basically say is that what we know about David Hume, yes, what we know about David Hume is different from Hume later conclusions. So what we know, we usually quote the treatise about human nature, that you can see causality in nature, but we usually ignore or we're unaware of the other later part that he said, listen, this thing is insufficient to describe the world.
Correct. Okay, which means the way we are taught in philosophy classes about Hume, we emphasize his constant conjunction, which is essentially another word for correlation, okay? And that's how he is registered in our mind, okay? But we don't read his revised version, which is relied on counterfactual. Now, what is counterfactual? Counterfactual relied on imagining a situation where you undo event.
I think that this is what you're looking for.
Yes,
if the first object hadn't been, the second had never existed.
That's right. We may define a cause to be an object followed by another. And listen to that now. And where all the objects similar to the first are followed by the object of the second, that's constant conjunction, okay? Yeah. Or in other words, he didn't even notice that he's jumping from something which is observationally verified to something which is totally hypothetical. Or in other words, where if the first object had not been, the second never had existed.
And this is plain causality. This is plain causality.
This
is 9 years after the treatise, and it was published in an inquiry concerning human understanding. 9 years later. And this is
yes.
like a mind-blowing thing.
Yeah.
Now, one thing that we need to set clear, because it is, I think it's a key element in your theory. Could you please explain to the general viewers what is counterfactual?
Yeah. Is a statement which conflicts with observation. I'll give you an example. I tell you, for instance, that had the train left in time, I would be able to attend the meeting and I would not be fired. Okay, which means I was fired. I was late to the meeting. My boss got mad, fired me. Now I'm saying something which did not happen. Had the train left on time, okay, things would have been different. And it goes all over. That's the way we communicate, both in literature and in science. We say, had the Cleopatra nose been different,
yeah, shorter or larger,
shorter, yes. The history would be different. Had Hillary Clinton won the election, okay, we wouldn't have that or that. We wouldn't have the Abraham Accord, okay. And we can look how clearly these sentences are, how they are understood by most people, how we form a consensus about counterfactual terms. Had Oswald not killed Kennedy, somebody else did, or somebody else would have killed him, okay? We communicate, we say yes or no, I believe you or don't believe you, and we form a consensus about. How can we do that about a world which doesn't exist? We're hypothesizing on words that do not exist, and we form a consensus. How is it possible? Only one way, that our understanding of the world allows us to compute counterfactuals, allows us to assign truth value to one counterfactual or the other. Okay. That is the contribution of some of my work here.
And can I, okay, but my question, which stay, can I use like the basic classic probability notation to describe counterfactuals? Let me give you like an example. Just a second. Let me, 10 seconds, okay? Okay, because usually, and I quote you, okay? So usually when we say causality in probability, what we basically mean, or intuitively mean, is the following: that the probability of A given B is, if the probability of A given B is higher than the probability of A given not B, then we say that with certainty B is one of the factor, one of the causal to A. And it intuitively makes sense. What's the problem with this way of thinking?
Okay, first of all, advise. Every time you find the word given, which is notated by the Bayesian vertical line, okay? Given B.
I love the vertical line.
Yeah. Every time you see that, you know already that the author does not understand causality. Okay? Which means you cannot express causal relationship with conditional probabilities. Why? Let's take the example of the rooster crow. Okay? The probability of sunrise, given that the rooster just made noise, okay, is much higher than the sunrise if the rooster did not crow. Okay? But that it doesn't mean that the rooster causes it. Okay? Summarizing it, probability language with its beautiful Bayesian vertical line, okay, cannot capture the idea of cause and effect. Okay. Shall I give you more example? Will example convince you or something, or a proof?
No,
I'll give you
because look, we have two ways of discussing this. One way is say, okay, this is like go to the core of philosophy. But I teach the course Bayesian algorithms for self-driving cars. And the textbook is called Probabilistic Robotics by Sebastian Thrun from Stanford University. He is the father of Google Car and Stanley. Now, he uses the Kalman filter, the Bayesian filter, all the Bayesian filter, all this, Yehuda, the vertical line, the probability of a position giving measurement from the sensors, and he did a great job doing this. So on the face, it seems that for many applications, probabilistic or conditional probability is sufficient to say where my car is given that my sensor or my GPS sensor got this position and my prior position was in T-1, something else. So my question is, and this is like a rude Israeli question, why does it matter? Because Sebastian used the vertical line over and over and over and over again, and he got to great results.
Yeah.
Is this a fair question?
Oh, absolutely, yes. You don't have to go to Sebastian. You could go to a guy that was born in Bnei Brak, Yehuda Pearl. Okay?
Bnei Brak? You were born in
Bnei Brak? Sure.
When was the last time that you ate chunt?
Oh, long time, because I think they removed all chunt from my street in Bnei Brak.
Wow.
No, just kidding. No.
I feel sorry for you.
Yeah.
Okay,
no, so
please give me an answer.
The answer is I was misled by the same siren song of Bayesian probability.
Siren song of Bayesian probability. You should be a poet. Wow, the siren song of Bayesian probability.
Well, you inspire me, you see. Yeah, for about 15 or 20 years, when I coined the name Bayesian networks, okay, and I advocated it in the time of expert system, okay, I was sold on Bayesian probabilities to be the final, what can I say, language in which you discuss everything. And I thought that causation is just a shorthand notation for patterns of conditional probabilities, okay? I was wrong. And the way I faced my wrong direction is when we had to deal with intervention. Or even before that, okay? We got rules like, I'll give you an example. If the pavement is wet, then it rained. Okay? Mm-hmm. If I break this bottle, the pavement is going to be wet. Now, take the two and say, if I break this bottle, chain them. If I break this bottle, then it rains. So dealing with a mixture of evidential rule and causal rule violates the law of chaining. With me? Okay. We noticed that already in the days of Bayesian network, okay? But we overcame it. So, which means for 20 years, we worked with the idea that Bayesian network is sufficient, not knowing that we, in the back of our mind, supplement its deficiency with causal models. So we had the intuition about the rain causing the wetness and the sprinkler causing the redness, yeah? And we thought we can express it in terms of conditional probabilities, and we don't need causation because we were so smart as to supplement the deficiency with a model of the world that we had in our mind. And Bayesian networks were successful because we were able to supplement it
And this is exactly what Gary Marcus says, that in artificial intelligence, we lack this causal model in our mind because artificial intelligence system lack these very causal models, and therefore many of the intelligence that they strive to are doomed to fail, because this is exactly what we lack, the causal model that we put into the Bayesian networks. Yes?
Correct. Absolutely. And I call it function fitting, which means the entire field of machine learning, of neural net, deep learning, are doing nothing more than function fitting.
Okay.
Fitting a complicated function with many hills and valleys to a highly complicated cloud of data points. Okay. But we can now today prove, it's not a matter of opinion, that I think that they are reaching the limit of their performance. It's a proof that you cannot get from this level of association into the next level of intervention and tell us what will happen if I tickle the rooster and have the rooster crow in the middle of the night, not in the early morning. Okay, I cannot infer that from my observation unless I do the experiment. Okay, so number one is jumping from association level to experimental level.
So let's go to this. This was my very next question about the ladder of causality. And this book of why you describe very nicely what we call the ladder of causality. So could you please help us in climbing the step by step in this metaphorical ladder? And let me just show it. This is the ladder. So we start with seeing, doing, imagining, and doing is like the intervention, and imagining is the counterfactual. So we had the train, got on time, I wouldn't be fired. And we start with association. And from what you write in the book, this is where Francis Galton stopped. He stopped at correlation.
Yes. Correct.
Okay?
Actually, he discovered correlation and was so excited that he forgot about the original question that he had. It was about heritage, the rules of hereditary, which he set up to do. Okay? What makes the son height depend on the parents' height? That was his original question. And he abandoned it because he discovered correlation and he was so excited.
So again, because we constantly hear in our academic training, correlation is not causation, correlation is not causation. And if you see correlation, it doesn't mean that you have causation. And sometimes there is like a hidden factor, etc., etc. And sometimes it's not that the low socioeconomic status that cause low intelligence, it's the low intelligence that cause low socioeconomic status, etc., etc. And those are inflammatory questions. But again, Galton set out to the scientific question was by its nature a causal question. What make people be genius? The study of the genius, this is what suit Galton to question. And, correct. Okay, so...
Well, he had good reason to ask it because he was a cousin of Charles Darwin.
The half cousin of Charles Darwin.
Half cousin, okay.
And so we have the intervention. And this is intervention. I do the experiment. And in this experiment, I can say, listen, this is not correlation. A actually causes B. Although that in a strict philosophical way, I cannot be 100% sure that A causes B. Am I correct?
You can be sure. If A and B are variables, then it's fine. You can say that taking aspirin reduces headache. Okay? And there is a causal relationship between the two. You submit people to aspirin. Half of them goes to aspirin, half of them goes to placebo, and you find that those who took aspirin improved their headache, as opposed to with a greater percentage of those who took placebo, and then you infer that there is a causal relationship between the two. Okay, not on the individual level. You cannot say my headache is gone because I took aspirin. Because on the individual level, it might be that the reason the headache is gone is because your wife gave you good news.
No, just a second. So what you just entered, or you just put on the table, the difference between the individual and the aggregate. So
absolutely.
Yes. So please, could you please elaborate on this? Why the difference? So if I take 100 people and 50 of them take aspirin and this lower their headache, and 50 of them take placebo and it doesn't lower their headache, so I can assume it's probability that taking aspirin has something to do with lowering the headache. Again, it could be like in a philosophical sense another thing, but usually we can say, okay, on aggregate it is true, but then you move on to the individual. Could you please elaborate on moving from the aggregate to the individual?
Very simple, very simple. Imagine that you run the randomized experiment, controlled experiment. You randomize people half here to half here, and you find no effect. Namely, the percentage of people who recover with placebo is the same as the percentage of people that recover with the aspirin. Good? Now, you don't know if it is the case that the aspirin has no effect of any individual, or whether it helps 10% and kills another 10%. Okay, so you don't know how it affects on the individual level. Okay, and that is a good example where we can never tell the difference between the no effect model and the help some and kill some model.
Okay, so let's go up the ladder. And right now we are doing counterfactual.
Counterfactual.
But in counterfactual, I can't do the experiment because this is like a Gedanken experiment. And then I take the aspirin. So my question is, when I do this thought experiment with the aspirin, where do I take my data from? Where do I take my hypothesis from? In the intervention, I take him from the experiment. We have 100 people. But in the counterfactual, it's like I come prepared, built in with this knowledge. But where this knowledge come from?
Okay, this knowledge comes from two possible sources. One, it comes from your perception of the world. That's your model. That's one you didn't like. You say it's subjective, okay? It comes from...
I like the subjective because in our daily life, when we talked about probability and odds, we only talk about subjective thing. We don't mean that we don't do like this cards example. Yes, what's the probability of a joker in the deck? We don't use what's the probability that they will get divorced? What's the probability that my father will die before 70? So we only think in daily talking about subjective probabilities.
And not only subjective, but subjective knowledge about the world. Knowledge is more than probability. That's what I was trying to convince you earlier.
Yes.
Because models of causation and counterfactual cannot be expressed in the language of probability. Okay, so assuming that we come out with that hypothetical model, or let's call it theoretical model of the world. It's hypothetical. Okay, that's one source. We are born with that. We demand it and we learn it very fast when we are babies. We satisfy this crave to have a deep understanding of the crib world. And deep understanding means having this set of functions that we call causal models. So that's one source. Okay? The other source is something which just in the past few weeks, I've been arguing with trialists that it's going to be a gold mine. It's going to change personalized medicine. And it is the idea that if you combine experimental and observational data, you can get information about individual behavior. Okay?
How?
How? Okay.
Just a second. And you said that you got it just 3 weeks, just before 3 weeks or 4 weeks.
No.
So, and you are 85. So it's not so simple. Yeah, it's not so simple.
I'm older than 85.
According to Wikipedia, you're 85.
Yeah, but I was born with Abraham, you know. So I carry on my shoulder centuries of civilization.
Definitely.
So, okay. No, the theorem was derived in 2001. Okay? But we just recently noticed that we are sitting on a gold mine, okay? And we are developing it. So first I have to prove to you by putting together biased, error-prone observational studies, okay, which are prone to confounding and all kind of, we're putting that together with experimental, we can get more information about individual behavior, okay, than each one on its own. I have to convince you on that. Would you like me to try to convince you?
I will like you that you make me part of this great gold mine. But yes, please convince me. Please convince. Let's start with you. Convince me, and let's move on.
We started with the idea that we observe now 10% improvement in both placebo and aspirin.
Okay.
And we don't know which model is correct. The one where the drug has no effect on anyone versus the model that says the drug kills 10% and cures 10%, okay? Now, just imagine that you have observational studies. And in observational studies, for some reason, people have a hunch of what's good for them. And they seem to never die. They always either take, what do I mean observation? Observational study is a study where each one can follow his own whims, his own free choice, okay?
Okay.
So people have learned whether to take the drug or not take the drug, and no one dies, okay? What does it tell you about individual behavior? About the model? It tells me that the model that says that the treatment has no effect on anybody is wrong. Why? Because observational studies say that choice makes a difference, right?
Okay, but then we can say, but why person A decided from hunch, gut feeling to take the medicine, and person B decided out of hunch, gut feeling not taking the medicine?
Absolutely.
And if we can formulate these hunch feelings, then we can say, okay, this is what a personal medicine is going to be all about, because I can fit, I can be the model can be this hunch feeling.
If I tell you that the person chose to take or not take according to what his cousin did, or what a rumor he heard in school, or what his family history is, then I would get myself into a difficult controversy with the trialist, because they don't like to rely on whims. The beauty of this is, regardless of the reasons, that the hunch-driven people acted differently, regardless of the reason, they give you information. And I can tell you, just by looking at their behavior, how good the information is there in their whimsical behavior. So I don't make any assumption about the reason that they act smartly or wrongly. I don't make any assumption.
Just on the fact that this was a free choice.
A free choice, and it's different than what we see in the experimental trial. Because in the experimental trial, we see no difference, right? In the observational studies, yes, we see smart people choosing correctly. We don't know why. I don't want to get into the reason why. It's enough that there is a difference between the two. It gives me information about individual behavior. And we have all the theorem and the bounds, and it tells you how much information you get, how to use it for advantage. How much information it has about individual behavior, whether you as an individual in the population, what chances you have to be harmed by the treatment or to be cured and saved by the treatment. That is the idea. No assumptions about the reasons why we saw the difference.
I need to think about it because, again, let's say that... Yeah.
I'll send you a new paper now.
Okay, because it's like, it's so mind-blowing because let's say that I have a hunch feeling that I want to take the medicine and say, okay, it's like a little placebo, okay? So I had this hunch feeling and then my body makes it better. But what does the model think? Because after all, when we finish everything and we are going to like produce a personal medicine virtual assistant, it's going to look at me and say, listen, you should take the medicine. But the act of taking the medicine from the observational study came from free choice. And free choice is...
Absolutely.
So it's a little bit challenging for me, but I strongly believe you. Now, I want to just go back 1 second to another very important idea for me. Now, you say that in Bayesian statistics, as the amount of data or observation grows, the contribution of the prior belief vanish and the credence become essentially objective. If I measure my position over and over and I get the same GPS location, so after 10 or even, I don't know, 5 consecutive independent measurements, the prior doesn't make any sense. And so I will believe the measurement. And this is basically the Kalman filter. Well, what you want to believe. You want to believe the measurement or you want to believe the prior. But you said, on the other end, the subjective component in causal information, which is a prior basically, doesn't diminish as the amount of data increases. And this is something which is A, profound, and B, I need you to explain, because when I teach my students about prior and posterior and say, your prior is that you are a good spouse, a good partner, a good boyfriend. Now, what do you need? How many measurements, how many girlfriends that say you are an asshole, I'm sorry, do you need to change your prior belief? Okay? So if one girlfriend, after another girlfriend, after a third, after 10 girlfriends say, you are a lousy person, you need to change your prior belief. But you said, again, that in the subjective component in causal information doesn't diminish. Why doesn't diminish?
I give you an example, but we want now to work on a scientific level, maybe equation, and not on the example level, okay?
Okay.
And why? Because the causal model is not vulnerable to refutation by the data, because it can fit any data. Okay, look, the model X causes Y can fit the same data as Y causes X. Is it clear? Are we in the same page when I say the model X arrow Y?
Yes.
Versus Y arrow X?
Yes.
Okay, now look at the two models and let's compare them. Is there any data where one model will be refuted by? Yeah.
No.
Okay. If the model is not vulnerable to refutation, how can you expect to eventually prefer one model over the other? It's undoable. Whatever data you give me, I can fit it that way and equally well by that way. Why?
Don't get confused by reality, basically. Don't get confused by reality. I can fit my model to whatever reality comes. And you say it in many political or philosophical discussions, okay? So I would like to take Bayes' law not to the sensor and the Kalman filter and GPS, but again, to something more profound.
Yeah.
So again, if you have like your viewpoint of life, you can explain using this viewport whatever data you want.
Because now you're applying Bayesian rule to a model. One model, not two events versus another event. See? Events are within the province of probability. That's where it works good. But now you're applying Bayesian rule to a model. Look at that, you have an error. Error is not part of probabilistic vocabulary.
You know, there is a great quote from Maimonides, the Rambam, which said that we need to strive for that our opinions will be influenced by reality and not reality to be influenced by our opinion. So I think this is basically goes nailed down what you said. Don't give me these subjective things that you can explain in whatever term because you came with a pre-built in inherent intrinsic viewpoint. Just listen to reality.
Well, not only listen, okay, but it's also the heart of Popperian philosophy that a theory is scientific if it is refutable.
Yes, definitely.
In this case, the choice between X arrow Y and Y arrow X is not scientific. It's becoming scientific if you have interventions in your hand.
And if you have causality.
Or intervention, if you experiment, if you can tickle X and see if Y changes, or tickle Y and see if X changes, that gives you a way to distinguish between the two models.
So because again, if I go back to your why I have Bayesian article, the reasons that you don't believe in C is a bad thing. So you feel sorry for yourself because people are like this. People don't diminish their prior as the data keeps coming in. But if I can just go one step further, they should, or if they would have diminished their prior when new data comes in, we as humanity, would have been in a different, better place right now. Would you agree?
Yeah, if the model was probabilistic, not if the model is causal. And look, religion is an example of a causal model, okay? Because God guides me, God tells me, God rewards me, God punishes me, okay? So here's an example where everything can be explained by Almighty God.
And moreover, the condition, according to the Talmud, a good condition in the Talmud, and you can think about it in terms of conditional probability, is if X, then Y, if not X, then Z. You must have these two things in a condition to be a valid condition according to the Torah, okay? If X, then Y, if not X, then Z.
Okay, but it doesn't follow the logic, because you cannot explain the difference between the two models using probability nor in logic, not logic. So you're saying follow is the logical thing. None of them. Classical mathematics cannot capture it. You need a new language, and that's the language of causal models.
Okay, and from this, let me go on. Can I ask you two more questions?
Shoot, I'm here to serve.
Oh, thank you so much, Yehuda. So what I teach data science. I teach introduction to data science and data visualization. What's your advice for young data scientists who listen to our conversation and wants to learn more about causality and want to implement causality in his daily work? Should he read the book of why, or if he reads the book of why, can he implement in his scikit-learn Kaggle competitions some of the ideas?
Well, you must start with the book of why,
which is a great book.
And I'm not Mendele Mocher Sfarim, which means I'm not trying to make money on the book sale, but you must read it to get the conception right. And then we have more technical introductory books. Primer is I forgot the name. The title is statistical. I forgot the name of the book, but I call it the primer. Okay, which is gives you. It's even taught in high school, and gives you all the algorithms there available for you to implement. And then we have a more in-depth book of causality, statistical. It's amazing if you forget the title of your own book. Okay.
Causality, inference. Your book is called, I wrote it down. Your book is called Causality, Models, Reasoning, and Inference.
Yeah, that's a heavy book.
But can I take your book, for example, the technical book Causality, and say, okay, when I do data science, when I have like a big pile of data and I try to find a model, to fit a model, to understand the data better, will I have tools, new tools? I know about correlation, I know about variance, I know about the Gaussian distribution, I know about Bernoulli, I know everything.
Forget it.
But will I have new tools that will give me new insights regarding the data?
New insights, absolutely, yes. Yes, and there are software now coming in by various people. Dagity, for instance, is a software available to everyone for free, which allows you to ask questions about graphs, causal question about graphs. Whether, for instance, whether a sufficient set of covariance is sufficient for adjustment so you can get the causal effect as opposed to a correlation.
Okay.
Adjustment formula. All kind of questions, once they are posed in the language of graph, can be submitted to the algorithms of Dagity. And new are coming now, new software platforms are coming in. Many machine learning people are shifting to causal machine learning or causal data science. Okay? Unfortunately, they have sold themselves so powerfully that all our education system is skewed on data science as opposed to data interpretation science.
So just Google causal machine learning and start from there. This is basically.
I heard something about it, yeah. And
this is fine because many of the models that we now hear or we now think about are not, can be interpreted just using probability or conditional probability or naive Bayes or all the other things. We don't have in current days data science, we don't use causality. We only use the Galton or Pearson correlation.
It is changing. It is changing.
Oh, this is a good thing. Now, my editor asked me to ask you, how would life look like today if Galton and Pearson didn't stop his correlation instead of continuing this original pursuit for understanding causal relationship? If Galton would have taken, the extra step toward causality, what would have happened today?
Well, I'm just stipulating, I'm not a futurist. So I would say that we'll have a better statistical understanding of the world. Statistics would not be such a dogmatic science. It would be more open-minded, and we would. Statistic textbooks will be totally different. They will be written.
I think that this is this is a sentence. Statistic textbook will be totally different.
Yeah, they will start with causal model, and then go.
Which is very intuitive because we think in causality.
Absolutely, and then within this model, they show how you handle correlation, as one step, the lowest possible step, how you handle intervention, how you handle counterfactual. And
again, counterfactual cannot be expressed using the language of probability.
Not only that, it cannot be explained also even using the language of intervention.
And this is why this is the highest place in the ladder.
That's why we have a 3-level, the highest step, yes.
So you're not a prophet, but nevertheless, Gary Marcus said one of the big drawbacks of artificial intelligence are the lack of causality. Would you think that this is something that is solvable, or like human beings, God gave us this very unique thing of causality, and it is very hard to formulate it,
oh no,
it's very easy. Just read the book of why.
Just read the book of why.
So in the next 10 years, we are going to see causality in artificial intelligence?
Absolutely. Absolutely.
And this will shift this entire field to new dimensions. Now, just blocked, since again, intelligence in some aspect of it means causality, and now we don't have this giant road that we cannot go.
Right. We don't have the vocabulary, and we don't have the way of thinking, at least not in the majority of data science scientists. Okay, and they have to be educated. And what happened? We made a mistake where we have invested all our societal resources in cathedral for handcuffed God. Okay, we built cathedrals, more than just cathedrals. If you look at your university, how much resources was invested in training, in data science programs. Okay?
I myself teach data science programs. I myself teach the vertical Bayesian law of conditional probability. I'm sorry, Yehuda.
Right. It's our mistake. We made a mistake. We invested too much in the low-lying fruits, and they're very rewarding. Machine learning is very successful, and but we made the swing is too much. We overdone it. And because we have overdone it, it will take a long effort and a hard effort to swing back to some balance, then to a hybrid systems, which involve machine learning together with the model of reality.
And again, let me just state it once again, the Kalman filter, the Bayesian histogram did great job. And if we restrict our conversation to self-autonomous driving car, no intelligence agents with counterfactuals, so this notion of probability and Bayesian probability and this vertical line gives us great results. But what you say that if you want to go to the next level, if you want to go or to gain bigger insight, higher intelligence, you cannot, this very low level, which yield great results, is insufficient for what we want from modern artificial intelligence systems.
Correct. And this is not an opinion, but a theorem. You must emphasize it.
Yes. And this theorem is well written in this new 2018 book of why. Why, Yehuda, this was mind-blowing. And I think that I will not give my student extra score for tattooing Bayes' law on their arm, maybe just the arrow of causality. This was such a mind-opening experience with you. Thank you so much for your time.
Well, thank you for the opportunity of addressing your students.
It's not my student, it's the educated, intelligent people of Israel.
Oh, and, great.
Yes. Wow.
Okay.
And we had, and I didn't talk about you about so many things. So maybe you will come back.
I will.
It was an amazing experience for me. Thank you so much, Yehuda. Thank you.
Thank you, Roy.
Bye-bye.
Take care.